This is the Fields Homework Booklet, question 24. So a straightforward point to start with: define the gravitational field strength and state whether it is a scalar or a vector. So gravitational field strength is equal to the force per unit mass. This is the statement that was required. I've just added a little bit of context that this is referring to a mass placed within a gravitational field. Since the field strength tells us about the force per unit mass, it will have a direction associated with it, and for this reason it must be a vector quantity. Next, a mass m is at a height h above the surface of a planet of mass M and radius R. The gravitational field strength at height h is given by g, and you are asked to, by considering the gravitational force acting on the mass m, derive an equation from Newton's law of gravitation to express g in terms of m, r, h and the gravitational constant g. This is not a difficult question, but I can see how you might get lost in the words here. So it is worth just letting your mind gather all the information together. I've done that just by sketching a little diagram there, and then going back to read the exact instructions of the question. It says, by considering the gravitational force acting on the mass. So this is where I've begun. I've begun with Newton's universal law of gravitation. And I've written that that force is equal to gmm divided by the radius of orbit squared. And notice there that you must add on the radius of the Earth to the height above its surface. So I've done the first part. I've considered the gravitational force, and now I need to derive an equation to form an expression for the gravitational field strength. It's not coincidence that in the previous part of the question you were asked to define gravitational field strength. So using that idea, gravitational field strength is force per unit mass, so I simply have to divide this expression by the mass of the satellite. Next, a calculation question. So we have a satellite of a given mass at a given height above the surface of Earth, and you are asked to calculate the gravitational force of the Earth attracting the satellite, giving an answer to an appropriate number of significant figures. This is a very standard equation and is really just checking careful substitution into the equation and the important point of adding on the height to the radius. This leads to an answer of 2.44 times 10 to the 3 newtons. Notice I had 3 significant figures for this height, and that is therefore the maximum that I can give in my final answer. Next, we have quite an involved calculation, which is why it is worth 5 marks, and it's important that you show every step carefully so that if you make a mistake, you can still maximise your overall score here. There are some alternative approaches that you can take to this question, so I'll show you one in detail and then refer to the others. So the satellite that we've previously referred to is in a circular polar orbit. You are asked to show that the satellite would travel around the Earth 3 times in every 24 hours. Now, thinking in reverse here, if you want to know the number of times that it's going to orbit in 24 hours, you're going to need to know the time period for one orbit. However, it's not easy to jump in straight away to that point. You might consider that the time period is 2 pi divided by omega, or you might use the alternative of 2 pi r, the circumference, divided by the speed v. So taking the first option here, you would consider the centripetal force first, and that equals m omega squared times the radius of the orbit. But again, always adding here height above to radius of the Earth itself. Rearranging there allows you to find a value for omega, which will be in radians per second. So carrying on from that, you can then move on to find the time period. So the time period is 2 pi divided by omega, and that leads us to an answer of 2.88 times 10 to the 4 seconds. Now, had you used the alternative equation here of mv squared divided by r, you could have found a value for the speed v, and then you could have put that into this equation, 2 pi r divided by v. It would lead you to the same answer. Now the final step is relatively easy. So the number of times that the satellite can orbit the Earth would equal the time available divided by the time for any particular orbit. So the time available is 24 hours, which I've converted to seconds here so that I can divide it by my value for the time period. And this gives an answer very, very close to the number of 3. Now, an alternative approach that you could have used in terms of setting out this would have been to prove and use the equation for Kepler's law. This is the equation that we had in question 23, and it shows that the time period squared of an orbit is proportional to the radius cubed. That's actually a derivation that's required on the specification, so you should be able to do it, and it gives you an alternative approach for finding the time period. The final step will then be identical. Finally, you're asked to state and explain a possible use of a satellite in the orbit that's been described. So this was a polar orbit. So it has the advantage that it is orbiting over the poles whilst the Earth rotates underneath that orbit. This enables the whole Earth to be scanned as it rotates. For this reason, this type of polar orbit is very good for monitoring conditions on the Earth's surface. It could also be used for spying, for example. But a nice easy example would be monitoring weather conditions. Those 2 points would probably have been enough to get you the marks, but it's also a useful point here to acknowledge that as the polar orbit is completed a number of times during one day, so information can be regularly updated.